Let's take a look at our banked turn scenario. So in this one, we're going to kind of break the rules a little bit with how we usually treat inclined planes. So we'll have an object. Here's our car. We're again assuming the car is like coming towards us here. And this car is once again horrible. It looks very angry. In the case here, what happens with a banked turn is that the normal force actually helps because it has a component, if we're looking at keeping horizontal and vertical as our x and y coordinate system. It has a component that pulls this way, and a component that goes this direction. And this thing here, Fnx, that is what is behaving as our centripetal force in this scenario. So let's take a look at our situation again. So in our x and y direction, starting with x, we have sigma F equals m AC. And a quick little aside over here, this theta in the corner, winds up in this angle over here. So if we were to draw out this component here, we could actually look at it like this. We have Fny coming up like this, and Fnx going this direction. So when we're looking at Fnx, because we're looking at the opposite scenario, we're looking at Fn sine theta, and that'll be equal to mv squared over r. And over here on the y direction, we have may, that'll be equal to Fny minus mg. Because ay is going to be 0 again, we do wind up with this, where we have Fny equals mg. Remember, Fny is the adjacent side, so that'll be just cosine theta. And then what Mr. Osmolinsky does next is kind of a little interesting. In the first units, we were able to multiply, add equations. What Mr. Osmolinsky here is doing is he's dividing both this equation by that one. Because these two things are equal, we're still allowed to do that. So let's kind of see what happens as we do this. We divide both sides by Fn cosine theta and mg. The m's cancel right off the bat, so do the Fn's. And sine of theta over cosine theta, that is equal to tangent of theta. So what we get is essentially tangent theta equals v squared divided by gr. And as we get a higher v, we do require, as a result of that, a higher theta to be able to compensate. So the angle needs to be steeper to be able to go around a sharper turn at a higher speed. Same thing, if we have a higher r, a higher radius, we will also need a smaller theta. So a more gradual turn requires less banking, which also makes some intuitive sense. As we go down a little further here, there are scenarios in which we would have a non-uniform circular motion. And this is an object that is traveling in a circle, but it's not going at constant speed. It's going at non-constant speed. That is going to cause the object to speed up or slow down as a result of its motion. And in our little diagram over here, we have our radius again. And if we're rotating in this direction and we're speeding up, that means we have to have an acceleration that is tangent to the curve. So a tangent. But we also have the acceleration going this direction along the radius that's keeping in this circular motion. So notice how the tangential acceleration, a tan. is pointed straight out from the curve and is responsible for changing the object's speed. The radial or centripetal acceleration, a rad, is responsible for changing the object's direction. So our actual vector for the acceleration will be going something more along this line to be able to get something to speed up. And that will need to change as our object rotates. So just kind of be aware of that. We won't be seeing too many problems that are non-uniform circular motion because they get a little funky pretty fast. So we're just kind of laying the groundwork here in the case that you come across this in college. As we scroll down a little further, Newton's law of, well, the next thing we're going to talk about is Newton's law of gravity. This thing's called the universal gravitational, or gravitation. So, there we go. And satellite motion. Newton developed the equation that directly shows the attractive gravitational force between any two objects. The formula for this is Fg equals big G m1, m2, all over the radius between them squared, where Fg is the gravitational force. As measured in newtons. Is a vector and its direction is along the line connecting the masses, so the radius in most of the cases we'll be talking about. Big G is the universal gravitational constant. This is just a number, and it's a number that Newton uncovered through some experimentation. This number is very small, but that should make some sense because to be able to generate enough gravitational force to be able to accelerate the things the way the Earth does, the Earth has a lot of mass to do so. And M1 and M2 are the masses we're talking about. So if we were going to talk about what is the weight of someone, one of those masses would be the person's mass. The other would be the mass of the Earth. So that's how that equation kind of plays out. And the R, once again, is the distance between the object, the first object, and the second object. And when we're talking about the Earth, it would be the distance between the person and the center of the Earth for the way this one kind of works out. So let's go on to the next page. All right. So in this question here, it says, example, find the Fg magnitude and direction acting on mass 1. So the situation here, we're going to have two different forces acting on object 1, which is this guy right here. We're going to have the force of gravity pulling from 2 onto 1. And we're also going to have the force of gravity pulling from 3 on 1 as well. And when we're done with this problem, before we're finished, we need to figure out what is the combined vector of the gravitational force. So we'll be looking for what is the sigma f when it's all said and done. And that also includes the angle. So let's use the gravitational equation to figure out what these two forces are, because we are given a lot of information. So looking at Ft1, or F2, comma 1. This one we have big G, and that'll be equal to mass 1, which is 4,500. Sorry, 44,500 kilograms. That's a big number. Mass 2 is even bigger at 650,000 kilograms. And the radius between them is 4.5 meters. And don't forget your square. Now, we don't want to forget what the big G is. Big G is 6.67 times 10 to the negative 11th. So if I plug into this equation here, I should be able to get a good answer. So 6.67 times 10 to the negative 11th times 450,000 times 650,000 divided by 4.5 squared. And we find that this first force is 0.005 0.963 newtons, and it's acting at 180 degrees because it's pulling directly left. All right. For the third one, 3,1, same scenario, but we are looking at 450,000 times 600, not 650, 950,000. This is even bigger than mass 2. And that'll be divided by 4.5 squared. All right, here, same equation, except our 650,000 becomes 950,000. And our radius, I messed that radius up. That radius should be 7.2 squared. This object's a little bit further over. And because of the increased distance, even though this mass is larger, we do find that the force of gravity acting on object 1 from 3 is only 0.55 newtons. Now this angle is a bit problematic because of the fact that, well, we don't know this thing's going either straight up or down, it's going at an angle. So to find that, we can do a couple things here, but if we're looking for this angle here, we can just use inverse tangent here. So we'll take the inverse tangent of 5.6 divided by 4.5, because we're looking at the opposite over the adjacent. And we get an angle of 51.2. And because it's 180 degrees, it's 51.2 degrees past that. So we'll add 180 degrees onto this and get an angle of 231.2 degrees. From here, we're looking at just a simple vector addition situation, and then we will have a final answer. So let's start this thing off with F21, 3. Might be a little bit rushed on space, but that's okay. I'll put the total up there, which is a little bit unorthodox, but space is necessary. So if I take the component of this guy here, I take 9.963 cosine 180, and I kind of obviously get negative 0.963. And in the y direction, we'll have a y component of 0 since it's not moving at all in that direction. On the other hand, over here, we have 0.550 cosine 231.2. We get negative 0.345. And for the y direction, same equation, just change this to a sign. We get negative 0.429. So adding things up, we have negative 0.963 plus negative 0.345. We get negative 1.308 and negative 0.429. So our sigma f, to start things off, we'll just use Pythagorean's theorem. So root 1.308 squared plus 0.429 squared. We get 1.377 newtons. And the angle, taking the inverse tangent of 0.429 divided by 1.308, we get 18.1 degrees. But because this thing is going to quadrant 3, we should add 180 to that, and we get an angle of 198.2 degrees. So that would be the combined force of gravity on this object. So we're going to stop there. We'll come back with 4 in the next video. So just scroll out of it and continue on.